Alright, yeehaw, boys and girls. Let's solve us some problems. Okay, this is force and kinetic energy, or work and kinetic energy number 1. Assignment 1. Problem 1. Alright, the only force acting on a 3 kilogram canister that is moving in an XY plane has a magnitude of 5 newtons. Canister initially has a velocity of blah 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 in the positive x direction, and sometimes later has a velocity of blah 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 in the positive y direction. How much work is done on the canister by the 5 Newton force during this time? Okay, so this is actually much easier than it might appear if you're new to this whole work kinetic energy thing. But basically you have this canister which has a mass of 3 kilograms, and initially it has some velocity v naught, I guess. What is this, like 7, what did we say, at 9 and 11? I already forget. Yeah, initially 9, then later 11. Okay. Equals, so we're going to say fine, initial velocity, we'll do it in vector form, is 9 meters per second, going that way, and it gets acted on by this force of, whose magnitude, well, let's see, acted on by this force, F, and we know the magnitude of F is 5.0 newtons, but, who knows which direction it's in, who knows how long it lasts, all that crap. But after it's done, V1 is 11 I hat, or 11 J hat actually, meters per second. So that's 11 meters per second in the positive y direction. The J hat is our unit vector straight up. So, in the beginning, this might look like, you might think, oh crap, I've got to do like, this goes through like this hyperbolic path or something like that, and I've got to figure out how long this force acts and exactly what direction and how much time this takes, and oh my god, this is a nightmare. But it's actually much, much easier than that. What this is simply a chance to use the work kinetic energy theorem for one object. So let's look at that. What this says is the change in kinetic energy is equal to the work done. And so the change in kinetic energy is the final kinetic energy, which I'm going to call EK1. Since V1 is our final velocity, I'm calling EK1 our final kinetic energy. Okay, minus the initial kinetic energy, which we're calling EK0, and that equals the work done by the force. Okay? Well, that's actually pretty simple. So we have a formula for kinetic energy, which is 1/2 mv squared, right? That's kinetic energy. Kinetic energy at position 1 is really, oh, that's not squared, that's squared. Is really just position 1, v1 is kinetic energy there squared, or so really these are vector velocities, and this is a speed. This is a scalar speed. It's kind of important to know. And so the initial kinetic energy is 1/2 mv naught squared, and that equals the work. So we just plug some numbers in here, and we can actually, simplify this a little by gathering terms. Okay. So now, what is this? 1/2 mass is 3 kilograms. 3 kilograms. Okay. Times v1 squared is 11 squared meters squared per second squared minus 9 squared meters squared per second squared. And that is the work. And so the, let's just do this. 11 times 11 is 121, right? So 121 minus 9 times 9 is 81. So it's actually going to be 40. And so it's going to be 40 in here times 1/2 is going to be 20 times 3 is 60. So this is actually going to be, work is going to equal 60, and it's going to be kilogram meters squared per second squared. Now a kilogram meter per second squared is a newton, right? So 60 newton meters, and a newton times a meter is a joule. So the work done is 60 joules. And that was remarkably easy. The fact that it's a 5.0 Newton force was completely irrelevant. The directions it was moving in at the beginning were completely irrelevant. All we need to know was the initial speed, final speed, and the mass of the object. In fact, we didn't, yeah, right, and the mass of the object, and then we could find out the work done in between the two. And there you go, that's the answer.